Hi, class. Welcome to physics for Tuesday, September 1st. Today, our video lecture is going to cover two topics. I want to talk a little bit more about precision and accuracy, and I also want to talk about a concept called Fermi problems, which hopefully you'll find a little bit fun. All right, so yesterday I talked a little bit about accuracy and precision. And I want to talk a little bit more about how they really are working when we use them in science. They both reflect how close a measurement is to an actual value. Both accuracy and precision do reflect how close it is, but they're reflecting that in different ways. And for accuracy, when we talk about how accurate something is, we're really talking about how close our measurement is to the known value, to that accepted correct value, if you will. One example we can use for this, I like using this in classes, is the idea of a bullseye. And if something has high accuracy, if an archer has high accuracy, then the arrows that archer shoots will be really close to that bullseye center, right? The center of the target. They'll be really close. They're hitting right where they want to hit. I want to contrast that a bit to precision. Precision isn't so much about being really close, it's how reproducible or how consistent the results are, right? So we could have an archer who is very consistent, right? Even if they're far from the accepted value. So instead of hitting that bullseye, having all their arrows hitting the bullseye, their arrows are all hitting almost straight down from the bullseye, like maybe 3 rings down from the bullseye, but they're all really close together. So the person's consistent, they're just not on target, right? And that's the difference between precision and accuracy, right? So we can be precise and accurate. We can be precise only. We can be accurate only. And we'll go through a couple examples here to talk about that a little bit more. So let's take this for one. Suppose I have 2 scales actually I have 3 in my prep room, but let's take a look at 2 of them. If I take a 50-gram standard mass, so we can have these little, we use them for calibration, and it's a 50-gram mass. So we know it is 50.0 grams. I'm being careful with my sig figs here. If I put that on my scale A and I take 4 measurements, 47.5 grams, 47.6 grams, 47.5 grams, 47.7 grams, what do we see? Well, we know that our scale is precise. And by that, I mean the numbers are all really close together. They're pretty consistent with each other, right? They're ranging from 47.5 to 47.2. There's only a 0.2 gram difference on something that's almost 50 grams. So it's pretty precise there. But it's not accurate, right? While those 4 readings, those 4 measurements are all clustered very close together, they don't give us the accurate number of 50 grams, all right? So the scale A, while it's precise, is not accurate. It's giving us the wrong number. So I take my mass and I move over to scale B. And we'll take some 5 measurements off of that scale. And what do we get? 49.8, 50.5, 51.0, 49.6. Now, if you take an average of these, let's see, 2, 6, and 15, we're going to get a little bit more than 50. We're going to get a little bit more than 50, but it's much closer to that 50 grams than scale A was. But the other thing I want you to see is look at the range in these. Our smallest number is 49.8, 49.6. Our largest number is 51. So there's a range of about 1.4 grams on this. So these, if you will, if I use my arrow analogy, these are kind of spread out a bit. So not as precise as scale A. But when we average the numbers, we're going to get closer to, if we average those 4 measurements, we're going to get closer to that 50 grams that we were looking for. All right, so again, just some more examples. I really want to drive home this concept of accuracy and precision. And there's a little note here at the bottom of the page. I'll talk about it more in the next one. But if we've got a tool and it's precise, right, we're getting consistent measurements with it. And it's just offset, like this one, the one at scale A here looks like if we add a little bit of mass to it, we can get not only keep our precision, but we'll get the 50 grams we're looking for. So sometimes you'll hear people talk about, has your instrument been calibrated correctly? Right? There's all sorts of times we'll use that. Police radar guns, taking your speed. You'll ask questions about how recent is the calibration? How do we know that your number is accurate? Okay. So let's talk a little bit more about how that really works when in science. So in science, in any measurement is inherently has some error. So how do we make sure we can minimize that error? Well, the first way we can do is we want to make sure we have the most precise tool. So if you remember from the graduated cylinder examples yesterday, we had one graduated cylinder that could measure to 10 milliliters, one to 1 milliliter, and another one to a tenth of a milliliter. So we want to use the most precise tool we can, which means the smallest increase in our reading, smallest increase in units between each of the tick marks on our instrument. Now, those tick marks could be physical, like they are on the graduated cylinder, or they could be digital, like they are on the scale, right? But either way, we want that smallest increment between readings that we can get off of our tool. We also want to make sure that we read our tool as precisely as it can get, right? It doesn't do any help us much if we have a tool that's precise, but we don't read it precisely. So how do we read a tool precisely? We're going to estimate that last digit. Now, if we're using a digital tool, there's nothing for us to estimate. But if it's something like a ruler or a graduated cylinder, we need to estimate that last digit ourselves manually. So how do we do that? Well, the way I like to do that is I'm going to look at it first. Where's the thing we're measuring? Does that part we're going to measure, does it fall between two? We're going to identify the two closest lines, right? And then where does it fall between those lines? Is it more or less than halfway between the two lines? So right away, let's say I have something and it's falling between our 49 milliliter line and our 50 milliliter line. I'm asking the question, is it more than halfway between the two lines? Is it closer to the 50 or is it closer to the 49? All right. And then further, I'll take one more step. All right, so let's say it's got, now that we know which one it's closer to, is it closer to the halfway mark? Which of the two closest lines is it? Now let's compare where it come to the halfway mark. So I can visually kind of identify where that 49.5, where that 0.5 tick mark might be. And I'm really asking the question here is, I have here further, is it closer to halfway between the 49 line and the 49.5 line? Right. So maybe if it's closer to the 49.5 line, maybe it's 49.3, 49.4. If it's closer to the 49 line, maybe I call it 49.1 or 49.2. So just by taking it and dividing it into quarters like that, do it halfway. Which side of that halfway line are you on? And to do halfway again, we can get pretty close to the accuracy of our instrument. We'd like to get it to about a tenth of that reading. So I just gave you a way to get within a quarter of the way between our tools, so 49.25. But we're going to estimate that last digit here. Well, 49.2 maybe, it would say, if it's less than halfway between our 49 and our imaginary 49.5 mark. And we'll do more of those throughout the year, but that's kind of what I was trying to do a little bit with those graduated cylinders in yesterday's video. And finally, the last point, if what we're measuring falls exactly on one of the lines of our measuring tool, that means our estimated digit is a 0. Don't forget to record that 0. If it fell right exactly on that 49 line, I don't just put down the answer of 49. Our answer is 49.0. Don't forget to put that 0 there. Use as many significant figures as your tool will allow. That gives you the most precise measurement that your tool can make. Okay. Finally, a little bit more about calibration. If we want to make sure, we could have a precise tool, like I was talking earlier about scale A, but if it's not calibrated correctly, that will not give us an accurate number. So we want to use the tool that has the highest precision, but we also want to make sure that that tool is calibrated correctly. And oftentimes that could mean something as simple as just adding an offset to it. In the case of scale A, if we added 2.4 grams to every measurement, we could get those measurements to be accurate. We just have some systematic error in our scale that if we calibrate it correctly, we can eliminate. All right. So I want to switch gears a little bit. I want to talk about one more example. This time I'm going to put a little bit of math in. So far I have been trying to avoid it, but I want to put a little bit of math in to try to drive that point home. So here's another example. We have accuracy versus precision example. We've got two students, and let's say those two students have taken some measurements, and they each took 3 measurements. So Rachel, so her first measurement was 11.32 grams per cubic centimeter. Second was 11.35 grams per cubic centimeter. And her third measurement was 11.33. So Daniel and Leah also did 3 measurements. Now we need to ask the question, which one is accurate? Which one's precise? And which one is both accurate and precise? So here I've got the data table here. And I'm going to tell you that the actual density of lead is 11.34 grams per centimeter cubed. That's our accepted value. That's the expected value for the density of lead. So looking at our results, which ones were accurate, which ones are precise, which ones are both? Well, if I ask you to do the math here, and I'm keeping the math simple, what I first want you to do is take an average. So we're going to take the average of Rachel's 3 measurements, 11.32, 11.35, 11.33, and I calculate the average, being 11.33. We're going to do the same thing for Daniel, getting 11.43, and the same thing for Leah, we're getting 11.31. So now we know their averages. What I want to do is take the average, because that's what we're going to compare to the actual value. The actual value. So we think the actual value of density of lead is 11.34. So if we look at Rachel, she got 11.33. She's pretty accurate. She was pretty doggone close, right? Daniel, a little bit off, right? Instead of 11.34, he got 11.43. And Leah's better than, is more accurate than Daniel, right? But not quite as accurate as Rachel. Okay. Now, if you look at those, let's see if there is some sort of offset for each of those, for each tool, each student. And if you look at Rachel, she's got some readings below. She's got a reading below the 11.33. She's got a reading above the 11.35. So her tool isn't just offset in one direction. Daniel's could be, right? 11.43, 11.44, 11.42. Maybe Daniel's tool is reading about a 0.1 gram too high, 0.1 gram per cubic centimeter too high, right? All his numbers are close, but they're all off in one direction. Leah, on the other hand, she's got numbers above 11.55. She's got a number below 11.04. So it doesn't appear that she necessarily just needs to shift her numbers. So when we're considering which one's the most accurate, we're just going to look at that average, and we're going to compare their average numbers to the expected result. In this case, we would say that Rachel is accurate. Let me move my mouse over here. Rachel is accurate. Daniel's a little bit off, so we wouldn't call Daniel accurate, but we'd call Leah accurate too, right? 11.31. She's pretty doggone close. That could be simply with estimating that last digit could put her off that much, but she's pretty good. Well, now we have to answer the question of precision. How do we get the answer? How do we answer precision? Well, precision, I want you to take a look at the spread of measurements. So look at that biggest measurement and look at the smallest measurement. So for Rachel, our biggest measurement here is the 11.35, right? And we're going to subtract the smallest one, 11.32. We have a spread here of 0.03 grams per cubic centimeter. We do the same thing with Daniel. Take the biggest one, 11.44. Take the smallest one, 11.42. What's the spread here? 0.02. But Leah, if we do that with her largest is 11.55. Her smallest is 11.04. She's got a spread of 0.41. So if I said this a different way, Daniel's arrows were hitting pretty close to the mark. They're all clustered together. They're all in the same spot, but they're all high. Rachel's arrows are also pretty good. They're all in the same spot, and they're right on, right? They're so close. Whereas Leah, her arrows are all over the place, but they're not off in the same. They're not all also not all clustered. So one's high, one's low, but you average them all out, and you get about the right answer. So we say, now let's go through and answer the precision question then. We're going to base it on that spread, right? Rachel, we're going to call Rachel pretty precise. She had a very small spread in her numbers. Likewise, we're going to call Daniel precise. Also a very small spread in his numbers. Leah, on the other hand, not so precise at all, right? Whoop, I have the wrong value here. This guy, this should be a yes. Sorry, Daniel is precise. So here I gave you 3 examples. Rachel being precise and accurate. Daniel being accurate being precise but not accurate, and Leah being accurate but not precise. Now that we were done with that little bit more on accuracy and precision, let's talk about Fermi, Enrico Fermi. We're going to talk about some Fermi problems here, but I want to give you a little bit of a background. Enrico Fermi, this picture here, he was one incredible scientist. Definitely, as I was going through school, college, graduate school, Fermi was one of the ones that I know I would always look up to as being an incredible scientist and one that was kind of very inspirational. So he was born in Italy, and what's really famous about him, one of the things that's famous about him, he did a lot, is at the University of Chicago. And this is during World War II. He created a controlled nuclear reaction. This had never been done before, and there are a lot of challenges to making a controlled nuclear reaction. That's why we see some of the nuclear power industry still a little bit shaky today, because it is very complicated. But he was able to make a controlled nuclear reaction. He did it underneath the soccer field at University of Chicago. They had built some tunnels down there, and they put it down there because the ground gave some shielding from the radiation. There was a great place is underground and away from everything else. So it worked well for him to do his lab work there, and he was able to accomplish that, the first controlled nuclear reaction. So that's part of the experimental side of what he did. Theoretically, he derived some properties of particles that we call fermions in his honor. Now, we might talk about them near the end of the year, but you guys are hopefully familiar with electrons and protons, neutrons from some of your earlier science classes. What I'll tell you is electrons are fermions. A fermion is a class of particles, and they behave in a very interesting way. If you remember a bit from your chemistry class, remember we did the electron configuration. We could put 2 electrons in a shell or an orbital, and this is why he told us we could put 2 and only 2, and his theory helped support that. Still a very, very pertinent, relevant theory that helps explain a lot in quantum mechanics. So there I gave you an example. He was a very good experimentalist, very good theorist. He was also a very humble man, very modest, not like some of the other scientists you might see who are very kind of pompous, if you ask me. But he was very good at being a real person. By the way, he died at the age of 53 from stomach cancer. And you might have heard this. A lot of the early scientists in chemistry and physics, especially in the early 1900s, before we really had a good understanding of the risks of radiation, often died of radiation poisoning because they didn't know that they were getting themselves next to something that was dangerous. All right. So that's a little bit of background on Fermi. But one of the things that he was also really known for was he could quickly make accurate estimates of things, which were probably actually they were very complex. And he could do this. He could make these calculations really quick. So you might hear me sometimes in class, and you might have heard others. Sometimes we call them back of the envelope problems. But what we mean is it's just you're sketching, you're brainstorming, you're thinking this, put them down. We're going to come up with an estimate of things. Sometimes they're called Fermi problems in his honor. So we're going to do a few of those today, and then I'll give you a few in a worksheet. We'll talk more about the worksheet tomorrow. So when you're doing a Fermi problem or a back of the envelope problem, we're not going for accuracy. We don't want to know a number to like 4 or 5 significant figures. That's not important. Really, we don't want precision. We're not going to 4 or 5 significant figures. What we want is accuracy. Is our number close to the right answer? So we only need 1 significant figure here to get that, right? If I ask, what's the average number of children in a household? I don't want you to come up with a number that says 1.738249. I mean, God, that'd be ridiculous. But how can we do something quick and easy that we can say, okay, we think the average number of children in a household is 1. And what's your process? How did you come to that estimate? So when we're doing these things, I don't want you using calculators. That kind of defeats the purpose. We're looking for something quick and easy. We don't need to spend a lot of time with calculators. And we don't want you using resources outside of what you already know, right? Because if you're using outside resources, then you can probably do it all that we can do it very exact, very precise. That's not what this is about. What I'm trying to get you to do is think in a mode where you can use your own knowledge and your own skills to quickly come up with an answer to something that's at least in the ballpark, right? So if I would have said the average number, if I would have said done one of these and I came back and I said, oh, the average number of children in a household is 100, you would have looked at me like I was nuts. Because I would be. There's no way it's 100. We know, just our gut tells us it's not 100. Now, one, our gut tells you that's probably not too far off. We're somewhat close. Maybe it's two, but we're at least in the right ballpark, right? And that's really what Fermi was after here. Can we get somewhat close? We don't need to be exact, but can we get somewhat close? And oftentimes you'll hear, besides back of the envelope, maybe it's an order of magnitude estimate. Sometimes we'll use that phrase, right? So like I ask you to estimate how many people are in the world right now. Hopefully you tell me somewhere around 5 billion. And hopefully you would know that 5,000 is nowhere near big enough and that 5 trillion is way too big, but something that you could get pretty close to the right order of magnitude. That's what we're looking for here. And Fermi did a great job of doing this. So let's look at a problem here. So the first one I want to try to do here is how many trees are used yearly to supply the U.S. with paper? So think about that for a moment. I'm going to pause the video here. I want you to think about that a moment. How many trees would you need? How many trees are used yearly to supply the U.S. with paper? So after you've tried this for a few minutes, open the video back up. All right, so here's what I want you to do to start. First, I want you to make a list. What facts would you need to know? What would you even have to do to come up with an estimate to what the yearly supply of U.S. paper is? And there are so many different ways you could do it. I'm going to show you the way my mind approached it, but you could approach it from a completely different perspective, and it'd be fine. Hopefully, we get very close to the same answers. So, from my perspective, is that what would we need? How would I even begin to calculate how much paper is used in the U.S.? So my first thought was, how many people are there in the U.S.? Right? So if I could figure out how much a given person uses, and then I know how many people there are, and I could keep stringing some of these things together and come up with an answer. So my first thought was, how many people are there in the United States? And I know it's roughly 400 million. And I say guesstimate because I don't know exact number is, but I know it's somewhere close to 400 million. It's not 40 million. It's not 4 million. It's not 200 million. And it's not even 300 million or 500 million. I know we're pretty close to 400 million of those numbers. So then let's think about this. How many pieces of paper does an average person use in the U.S. each day? And I said, okay, well, it's kind of hard, but 20 pieces per day sounds at least reasonable. Between the letters you get and things that you write in school and all the people that are doing things, but just as many people are in school where you guys are getting lots of paper a day, there are a lot of people who are not in school who don't use a lot of paper a day, right? So just tried to pick something that seemed fairly reasonable, but hopefully close. I meant to erase that first one of the guesstimate of the 400 million because I wanted to start there. Here with let's first start with how many pieces of paper does an average person use? Guesstimate 20. Well, how many people are there in the United States? We're going to guesstimate there's 400. So now we have an idea of how many people and how many pieces of paper we're using per day. Well, how much does a piece of paper weigh? So I'm going to guess it's about 0.04 pounds. I'm doing that thinking that a ream of paper, I'm going to guess is around, has 500 pieces of paper in it. I'm going to guess that because they call it 20-pound paper, that it's 20 pounds for a ream. So if I take that 20 pounds divided by 500, come up with 0.04 pounds for a single piece of paper. All right, so you can see I'm trying to build a calculation here. How much paper does a person use? How many people are there? How much does a piece of paper weigh? Then I started thinking a little bit about this. What percent of a paper's weight comes from a tree? I would assume that it's a pretty big number, but not all of it. So maybe there's some other stuff they mixed in there to kind of bind it together so it's not just a mess. Maybe there's a coating on it so that it copies nicely. So I just estimated 95% of the paper's weight comes from a tree. And let's see, what percent of a tree is used for paper? Well, we don't use the roots. We don't use the leaves. I don't know if we use the twigs and branches or not. So is it okay? Maybe we use 80% of the mass of the tree as we're making our paper. Now, each one of the numbers I've given you so far, you probably could say, okay, yeah, maybe it's not exactly right. But you gotta, hopefully you're like me and your gut feel is, yeah, that's reasonable. And that's really all we're looking for. So another question we need to answer then is, what's the average weight of a tree? So if I'm just going to guess that average tree that we use to take to the paper mills, I'm going to guess it's about 1,000 pounds. I know it's not 100. I know it's not 10,000. Is it 500? Well, 500 might be a small tree. I don't know how big the trees are that we use for it, so I figure 1,000 is at least close. Okay, so now we got to put all those numbers together. Let's put all those estimates together. So we started off with 400 million people. Each person uses 20 pieces of paper per day. So I've got this factor here is 20 pieces of paper per day per person. So what I want you to see here, and I'm going to kind of cross these out as we go through it. Let's see, what color? I don't know, we'll use black, right? We're going to use black. So I've got people here in the numerator. I got people here in the denominator. So those units are canceling each other out so far. Right? Well, the question was in a year. So we need to, how many days are there in a year? 365 days in a year, because we got 20 pieces of paper per day, right? We need how many days are there in a year? So now we've got 365 days in a year. I got days in a denominator here, days in a numerator here, so they're canceling each other out, right? And next piece was, how much was each piece of paper weigh? I'm guessing 0.04 pounds of paper a piece. The next factor we thought about, okay, so how much of that pound of paper, what's the ratio? How much tree pulp do we need to make that pound of paper? And we said that 95% of the paper comes from tree pulp. So I put 1 pound of paper creates 1 pound of tree pulp will create 95.95 pounds of paper. All right. So again, now I'm crossing things out. We have a piece here. We have a piece here. We have, let's see, pounds of paper here, pounds of paper here. The next thing was, well, how much tree pulp does a given tree create? And I said, okay, well, I think a tree is, up here I said 80% of that tree is used for pulp. So 1 pound of a tree will give me 0.8 pounds of a tree pulp. So I got tree pulp over here, pounds of tree pulp over here, numerator, and pounds of tree pulp in the denominator. So I'm going through and showing you how the units cancel out. I'm doing that so I make sure I'm putting things in the right place. I don't have one of these things flipped over, like it should have been 0.8 pounds tree pulp over 1 pound of tree. No, because my units wouldn't cancel out. Okay. And finally, we have our last one. It says 1 tree. How much does a tree weigh? It weighs 1,000 pounds. Well, 1,000 pounds of tree, we're going to cancel out that pounds of tree there. What are we left with here? What are we left with here? The only units we're left with is in the numerator, we have trees. The denominator, we have years. That's what the question asks us for. How many trees per year? So now we just have to punch these numbers together. 400,000 times 20, multiply it by 365. I guess if I really wanted to be accurate, I would have just said, let's make it 400 so I don't need to use a calculator. And then a 0.4 here. Probably should have kept all these numbers to just one significant figure to really be consistent with what Fermi was doing. But since we knew this number exactly, I just kind of threw it in. So if we multiply all these numbers together, what are we going to end up with? 1.5 million trees. And I should have put on here per year. 1.5 million trees per year. So that's my ballpark estimate. Hopefully you got something close. So what I'll ask you to do, why don't you put your estimates for these into our question for the week, just to see what everybody was getting, what we're all at. And then later on we can actually Google it and find out how many trees a year are used for paper in the US. All right. So I got another one here we're going to do. How many dental hygienists work in Westerville? So I want to follow the same kind of an approach. Now, typically, I try to go all the way back to the beginning. You may choose to work the opposite way, start from the end and work back to the beginning. Whatever your mind works, it doesn't matter, just as long as you have a logical thought process. So I started this off, well, if I want to know how many dental hygienists work in Westerville, what do I need to know? I thought, well, first we need to know how many people are there in Westerville. And I'm going to guesstimate that there's about 40,000 people that live here in Westerville. And next question, what percent of the people see a dental hygienist? Well, I know that my family, we see it all the time, but I know I've got some relatives that haven't seen a dentist in 30 years. So I'm going to guess that maybe 60% of people see their dental hygienist. And then the next question, how many times a year do they visit their dental hygienist? I know I visit them twice a year because that's the way I was always brought up. You visit your dentist twice a year, keep your mouth healthy, your teeth healthy. So now that if we know how many people there are, how many people, what percent of them go, and how many times they visit a year, well, we've got the number of visits, but we need to know a little bit more. How long does each one of those visits last? Right? I know from personal experience, it's about 1 hour. Actually, I'm going to change this. I think I put 1.5 below. About 1.5 hours. So I might be in the chair with a hygienist for an hour. There's paperwork and other scheduling challenges, logistics. So maybe it's really about an hour and a half they average per patient. And then how many hours in a year does a dental hygienist work? So how many hours do they have available to see people? And I'm going to guesstimate 2,000 hours per year. Think about it. There's 52 weeks in a year, which just round that to 50 to be nice and to allow vacation time. 40 hours in a week, 40 times 50 gives you 2,000 hours, work hours in a year. So let's put all our calculations together. 40,000 people, 60% of those people, so 60 people out of 100 will see our dental hygienist. Of the people who visit the hygienist, they visit them twice a year. So let's go through and start crossing them out. So there's 40,000 people. I got those people on the top. There's people here on the bottom. These are the people who see the hygienist. How often do they see the hygienist? 2 visits a year. So I got people seeing a hygienist, people seeing hygienist, top and bottom. They're going to cancel each other out. Now, how long does each visit take? 1.5 hours per visit. So here we have visits in the numerator and visits in the denominator. So now we're setting those up right. And finally, how many hours does a given hygienist work in a year? How many hours does a hygienist work in a year? And so we're going to take the hours from here, and they're going to cancel out the hours from here. So now a hygienist works 2,000 hours per year. So I'm going to cross out that year here and that year here. All of our units have canceled out. Well, because we just asked for how many people how many hygienists do we need? So we multiply all our numbers together. What do you come up with? I came up with about 36 hygienists would be needed to handle the people of Westerville. Again, I have no idea how accurate that number is, but all these estimates I put together here were reasonable. I think we could say, definitely in the ballpark of 40,000, 60%, et cetera. That's what we mean by Fermi questions. I want you to come up with, if I give you a question, what are some things you would want to know to make that calculation? And what are some reasonable estimates for those things that you would need to know? Okay. So I've given you 2 examples. I want you to take a look at the Fermi question worksheet in today's folder, and we'll talk about it more tomorrow. Thanks, everybody.